Hi, thank you for having me. My name is Katie London. I'm going to be talking about this topic. I should say what I am, I guess. I am a shortish woman, Caucasian, with an asymmetrical featured face. And I'm a New Yorker, in case that conjures anything also. And I'm grateful to be here and to talk with you guys, and also grateful to hear all the amazing talks that have already been today. It's really an inspiring group of people, inspiring work, and great provocations for all of us. So today I'm going to speak about, and forgive me, I'm going to refer to my notes from time to time. But I'm going to talk about this topic, which is wrist-based surface electromyography as a novel XR human-computer interface controller in the context of accessibility. And in order to get to the accessibility part, I want to make sure that you understand what the technology is and how it works. So I'm going to talk you through and show you some videos so that we all have a shared understanding of what we're talking about here. Make sure I can advance videos here. And before I jump in, I just wanted to say that I'm speaking on behalf of our group, which is within Meta Reality Labs, which includes research and product groups that work on things like VR and mixed reality and Ray-Ban Meta glasses. And you see this little image on the right side of the slide says Control Labs. I'm speaking to you from that little corner of the universe today. That was a company that was acquired by Meta in late 2019. And so I'm going to talk to you about the technologies that we've been developing within that context. And just context on me, about 20 plus years developing Gen 1 technologies for hardware and software. All right. Okay, so the first thing to know is that electromyography detects electrical signals which are produced when users initiate motion in the body. So before we dig in, I just want to say that EMG is not new. A lot of times people talk about technologies, it's all about the shiny newness, and I think it's important to acknowledge history also. So this technology has been around for some time. And when the team at Control first started working on this technology, it was probably the least sexy thing in neuroscience. The periphery of the body is not necessarily always so interesting. But that's where we started, mechanistic neuroscience that starts at the muscle. So what we focus on specifically is wrist-based surface electromyography, or sEMG, and I'll show you some videos of what I mean by that. But just to be clear, that is a technology that uses sensors placed on the wrist, on the skin around the wrist, just like, a band of a watch, for example, to detect electrical signals that are produced when a user initiates movement at their hands or their fingers. These signals are generated by the neuromuscular system and then are translated into digital commands for device control. Okay, so let's go a little bit deeper on that history. So some of you may be very familiar with surface electromyography, but for those of you that aren't, it's been used in clinical and lab settings for decades. This has been complicated as it requires often custom hardware, sensors, or electrode placement, and bespoke model or algorithm development that lacks scalable data. So not super reproducible at scale. And sEMG has been a really important part of input for developing controls for prosthetics, amongst other applications. In this picture, you can see that's the Myo band, if you're familiar with that. So I'm going to refer to the work that was published recently in February on bioRxiv from our group. And I hope it's not too dry and scientific, like Dylan talked about earlier. I hope I can make it even more sexy and exciting for you guys, so it's engaging. But we've been researching kind of advanced neuromotor interfaces as an XR input device to do things that you might use a touch screen or a handheld controller or a keyboard for historically. As I mentioned, we recently published our first public paper, and after about a decade of research, so it's pretty exciting for us. And that's what I want to talk you through today. So this video shows, it is linked from that publication, and it shows our research device for generic neuromotor interface for human-computer interaction. So you can see the person's making light gestures with their hands, and these rainbow colors correspond to the sensors. And that shows you the kind of rich data and rich information and signal that we're able to obtain from just wearing a band at the wrist. Now, if we pair that with an interface, you can see here how you can apply some of those signals, swiping, tapping, et cetera, of hand gestures to control and navigate through an interface. And this is another example showing continuous one-dimensional control as well. Also, just simply using the signals from that wristband. And here you can see how the same research device and technology can be used to enable even more rich control for text entry. In this case, it's handwriting. So the person's using their index finger as you would a pen to write characters, and then it's detected in the system and understood. Another example of text entry, and this will be the last one that I show, then we'll get into some more of the nitty-gritty details. This is a person wearing two of the same research device bands and using their legs to type as if they would on a QWERTY keyboard to quickly enter text, but they're not at a desk, they don't have a keyboard, they're just using whatever surface is there. And we do know a lot about the motor system and how it's controlled. And if you want to know more about this, you can kind of reach out to me after. I'll quickly touch on some of the top line research innovations that enable calibration free. And what I mean by that is like generic, meaning you don't have to necessarily train a model yourself. So calibration free sEMG neuromotor control. It spans things like hardware, data collection, and software. So this shows sort of and all of this is referenced in the paper, so you can read more about it, but this shows like a quick evolution of some of the devices that we developed, research prototypes, to get to a kind of single form factor, which is what we cite in the paper. And that includes things like, connectivity and also electrode placement, like sensor placement. Again, this is non-invasive. This is just something you wear on the outside of your skin. But by understanding and evolving sort of the sensor design, the placement, the materials, it allows us to get to clear signals of motor unit activity so that we can detect clear signals in order to use them for input, as well as make sure that we have comfortable and easy donning and doffing. Again, this is a research prototype, so I just want to make sure I'm really clear on that. And the research paper also highlights our approaches to establish generalized models, leveraging more than 10,000 diverse participants' data. And this is just a subset section of some of the diversity dimensions. We also talk about how we collected that data. What does the setup look like for participants? And what does it mean to perform the gestures, and how do we describe those to individuals who are participating so that we can scalably build such systems? So the research took an alternative approach by evaluating models trained on many users, including models of different size. So with a much higher scale of participants than has been historically possible, right? I talked about historically what that looked like with bespoke models, bespoke placement of electrodes, for example. This data observes similar power loss scaling as other forms of machine learning, like computer vision. So the key result here is scaling to thousands of users improves model performance, indicating that the models learn representations invariant to the unique participant level sEMG signals due to anatomy or physiology or behavior, or even environmental and donning location factors. And that's pretty exciting for our team when we think about designing for everybody. And actually, I want to step back and talk a little bit about some of the responsible innovation principles at Reality Labs at Meta, because I think that's an important component of this and an important component of why I'm grateful to be here today to talk to you guys about some of this work that we're doing. We have Reality Labs wide responsible innovation principles. These are them to help guide our work. Now you can see these are very high level, and that might seem naive, if you will, but they're high level on purpose because the idea is that everybody should memorize them. They should be a part of the development for every researcher, every scientist, every QA person, every designer, wherever you sit in the process of developing these technologies, so that for the decisions that you make, you have a lens to look through and evaluate how you're being accountable to those principles. And one that I wanted to zoom in on a little bit and then show a little bit more on is considering everyone, which is relevant in this context. And I thought I'd give you a little bit of a timeline of some of the way in which we've been invested in this. So given that there's like a huge opportunity as we see it in terms of the rich potential of this input technology in affording participation and engagement and control for people. Responsible innovation has been a part of our R&D process since the early days. So I mentioned Control Labs was acquired in late 2019. As early as 2020, we had our first responsible foresight workshops, really digging in on what are the core priorities, what are the principles, what are the risks, how do we focus on this? Back in 2021, we put out a call and funded, there was a request for proposals on engineering approaches to responsible innovation for surface EMG interface design. We funded 6 external initiatives. Those are unrestricted grants so that those folks could also publish and kind of push forward the industry. And those explored things like considering everyone by promoting inclusivity in system design, putting people first by treating data with care, providing controls that matter by developing tools and methods for data management and privacy. And there's a few up here, and papers have been published. So that work is out there for others to build on and engage with. Then in 2022, we really sort of ramped up our extensive data collection, including diverse physiological representation, but also environmental and behavioral conditions, because again, we want to think about considering everyone here. In 2023, we engaged in 3 global roundtable discussions with external policy and academic experts and advisors on different dimensions of this technology to solicit feedback early and often. So the idea being, like, as I think was spoken to in multiple of the speakers before me today, is the importance of bringing other voices into the conversation, not working and developing in an isolation chamber, if you will. And an important dimension, before I kind of play this video, I just want to like set the scene a little bit for it. An important dimension of considering everyone, it is about people representing a range of motor abilities. So we've heard about different abilities today, and here I'm largely talking about different motor abilities or amputees, for example. So this is a video of a colleague who's given us permission to share this video, Anton, and he's trying out the research prototype for the first time in this video. So it's the first time he's put it on his body, and there's a few points I want you to keep in mind when you watch it. He lost his hand when he was 7. In this video, he's an adult, and this is the first time he's put on this band. We haven't done any data collection or training of the model on his body or data from his body. And the only instruction he's given is to perform an index and thumb pinch, just like this, and hold it, and then kind of move his arm or move his wrist to play a game to kind of slingshot a shape, a yellow shape, which I'll point out to you when we show the video. That's all he was instructed. And so you'll see that he's missing this hand, but he's able to regain use of control of an index and a thumb pinch in the digital game here the first time he puts it on. I think what's most important, and this speaks to some of the points that Meryl, and I think, I'm sorry if I get the names wrong, but Sunny and Jesse were talking about earlier in the first session today, is that what's the most important thing for us as developers creating this, as researchers, is really the delight and empowerment that we see in his response in the experience. So why don't I play it and make sure that you can see it. Okay, so you see that's the band on his, a little bit higher up than his wrist, that yellow object. He's pinching, so when he lets go, it knocks down. You can see he does it again. So he's doing another pinch. If the video was a higher resolution here, I'm sorry, I don't know. I think it's because it's playing off my computer. You would see that there is some visible movement in that part of his wrist area. But you see he doesn't have a thumb or an index finger, but he's able to perform that action. And he tries it again and is able to do so. So, when we think about considering everyone, we can see here how this wrist-based sEMG research prototype can enable kind of inclusive design for a population. I'm not saying every population, he has an arm, but for a population that might struggle with other interfaces. Computer vision hands, for example, if you don't have the hand there, that could be more difficult, for example. Move to the next slide. Great. So in addition to the RFP in 2021, we also continue to partner and support initiatives to advance the state-of-the-art, leveraging this research device and tech to enable people with a range of motor abilities. So I wanted to talk a little bit about some of the work that we're doing in that space. 3 examples, a subset of a few. On the far left, we have one range, which is no movement, paralysis, or amputation. And so this is work that we're doing, supporting with Carnegie Mellon University, enabling their team to explore how fully paralyzed patients with perhaps 1 or 2 remaining motor units in their arm can use the device to regain controls virtually. And in the middle, there's an example of a patient with stroke or muscular dystrophy. They're using the system so that in this case, the patient can't unfurl their hand in the real world. However, you can see from on the screen, the patient regains that capacity to do so. Then all the way on the far right of the screen, we're exploring how this research device can enable people with excessive movement. So no movement on the left, excessive movement on the right here, who might, for example, just as an example, it might be somebody who ages out of the ability to control a touchscreen phone, for example. Maybe they develop Parkinson's or they have essential tremor. So how might this technology be able to kind of recognize and enable control for that population as well? So as we look to the future, there are definitely more opportunities to explore moving from a kind of low bandwidth naturalistic control to more high bandwidth, always available control across populations with diverse motor abilities. You've seen in the early videos that I showed in this presentation, how more lightweight interaction can enable kind of like more effortless control. And you saw how it doesn't have the restrictions that some technologies might have. Most notably, wrist-based EMG allows us to kind of create interactions that can be used by people of varying neuromotor abilities and can be used on the go, as illustrated here. So our research has been able to kind of generalize, has been able to drive higher bandwidth, complex multi-joint behaviors can be modeled as well, like typing, which we looked at. And we can also kind of follow on to work from 60 years ago to create a motor unit button for simple games. This is not showing the video that I want it to show. So let me see if I can click on it. Oh no, it should be showing you a little game where this person is making very little physical movement that you can't really see, but they're able to, oh, there it is. They're able to control this little character with these subtle movements. And our research in that research device is allowing us to sort of detect those. So, you've seen how that could be applied for folks with paralysis, but there's other explorations as well in terms of how to support a range of neuromotor abilities. We really think that there's a lot of great opportunity here, and we want to make sure that we're considering everyone as we're on that journey of research and development. The last thing I want to say is that it takes a village to make these things. So, though I'm standing here speaking to you, I'm representing many human beings who came together to push the bounds of what's been done before in hopes of making something better for the world. So, um, I will leave it at that. I know we were a little behind on the schedule. Yeah, thanks.